Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at Group 2 of the periodic table, the alkaline earth metals. We're going to talk about what the Group 2 metals are, their trends in atomic radius and first ionization energy down the group, how their melting points change down the group, and their increase in reactivity, as shown with their reactions with water. For revision videos of the specific reactions needed for each exam board, please check the links in the description below. Before we talk in detail about Group 2 metals, there are a couple of essential ideas you need to be comfortable with. Atomic radius is used to describe the size of an atom. It refers to the distance between the nucleus of the atom and its outermost electrons. In simple terms, the bigger the atomic radius, the bigger the atom. The first ionization energy of an element refers to the energy required to remove 1 mole's worth of electrons from 1 mole's worth of gaseous atoms of an element, forming 1 mole's worth of ions with a 1+ charge. The higher the first ionization energy, the harder it is for an atom to lose an electron, and the lower the first ionization energy, the easier it is for an atom to lose an electron. Recap done? Let's go! The Group 2 metals are the elements in Group 2 in the periodic table, and are beryllium, magnesium, calcium, strontium, barium, and radium. They are also called the alkaline earth metals. Alkaline as their compounds tend to form alkaline solutions with a pH greater than 7, and metals because, well, they are metals. As they have only 2 electrons in their outermost shell, they commonly form ions with a 2+ charge. As you go down the group, the atomic radius of the atoms of each element get larger, meaning the atoms are getting bigger. This is because there are more inner electron shells, increasing the level of inner electron shielding and forcing the outermost electrons to be further from the nucleus, increasing the size of the atom. Another important trend of the Group 2 metals is that melting point decreases as you go down the group. To explain this trend, we need to remind ourselves that in metals, atoms are held together by metallic bonding, described as positively charged ions attracted to a sea of delocalized electrons. To melt a metal then, these forces of attraction between the positively charged ions and delocalized electrons need to be overcome. And the stronger this attraction, the more energy that is required, and the higher the melting point of the metal. A high charge to mass ratio of the positively charged ions means stronger attraction. Essentially, the bigger the charge and the smaller the ion, the stronger the attraction. Group 2 metal atoms all form ions with the same charge, 2+. However, the elements at the top of the group have a much smaller atomic radius than elements at the bottom, meaning the nucleus is closer to the delocalized electrons, increasing attraction to them and giving stronger metallic bonding, increasing the melting point. For example, beryllium has a high melting point of 1511 Kelvin, and barium is much lower with a melting point of 998 Kelvin. Magnesium actually has a lower melting point, 922 Kelvin, than calcium, 1112 Kelvin, meaning magnesium doesn't follow the trend of the other Group 2 metals. This exception is generally believed to be due to magnesium atoms being arranged in a slightly different way to the other Group 2 metals in a solid lattice, decreasing the level of attraction between the positively charged ions and delocalized electrons, making the metallic bonding weaker, giving magnesium a slightly lower melting point than we would expect. As well as melting point, as you go down the group, the first ionization energy of the elements also decreases. This means it gets easier for the atoms to lose an electron and form a positively charged ion. Again, this is because there is an increased level of inner electron shielding, meaning the outermost electrons are further from the positively charged nucleus and experience less attraction to it, meaning they're easier to remove. For example, the first ionization energy of beryllium is 900 kilojoules per mole, whereas for barium it's only 503 kilojoules per mole. There is actually a very slight increase in the first ionization energy between barium and radium. However, this is due to something called contraction, which is often seen with much heavier elements, where the nuclear charge becomes very large. This isn't examined at this level, however, you don't need to worry. The only reason I'm telling you this is that don't be surprised if you see a slight increase between barium and radium in data tables and graphs. This all causes the reactivity of the group 2 metals to increase down the group. When metals react, they commonly lose their outermost electrons from an S subshell, forming positively charged ions. And as we've seen, it gets easier for the group 2 metals to lose their outermost electrons as you go down the group, shown by a decrease in first ionization energy. This means as you go down the group 2 metals more readily react, making them more reactive. We can see this trend in reactivity by looking at the reactions of the group 2 metals with water. The general reaction for a reactive metal with water is metal plus water forms metal hydroxide and hydrogen gas. For group 2 metals, because they form ions with a 2+ charge, the metal hydroxide formed contains 2 negatively charged hydroxide ions, OH-, given a formula of MOH2. With 2 molecules of water needed per metal atom in the reaction. Beryllium at the top of the group doesn't react with water. Going down the group, magnesium reacts very slowly with cold water, forming magnesium hydroxide. Magnesium can react with hot steam, however, very quickly, forming magnesium oxide and hydrogen gas. Mg plus H2O forms MgO plus H2. For the rest of the group, calcium, strontium and barium, they all react with cold water easily, forming their metal hydroxide. The reactions become increasingly vigorous and intense down the group, showing that the metals are reacting faster and more readily. They are more reactive. So, to summarize, atomic radius of the group 2 metals increases down the group, as there are more inner electron shells, meaning the outermost electrons are in subshells further from the nucleus. As a general trend, melting point decreases down the group because the atomic radius increases. The positively charged ions in the metal have a lower charge to mass ratio, and there is weaker attraction between them and the delocalized electrons in the metal, meaning the metallic bonding becomes weaker. Magnesium is an exception to this general trend, and this is believed to be due to a different crystal structure and arrangement of ions in magnesium compared to the other group 2 metals. First ionization energy of the group 2 metals decreases down the group, as there are more inner electron shells, meaning an increased level of inner electron shielding. The outermost electrons have less attraction to the positively charged nucleus, and it is therefore easier to remove them from the atom, meaning first ionization energy decreases down the group. Reactivity of the group 2 metals increases down the group. This is due to the outermost electrons being more easily lost, and therefore the metal atoms can react to form positively charged ions more easily. This can be seen with the reactions of the group 2 metals with water, forming metal hydroxides. Beryllium is unable to react with cold water. Magnesium only reacts slowly with cold water, and calcium, strontium and barium all react with increasingly vigorous reactions with cold water, showing an increase in reactivity down the group. I hope you found this video helpful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.